Right, so this is a part of the topics I wanted to cover today. I wanted to finish off our discussion of binary operations with an example. I also wanted to do a few further examples related to the type we would have met in our last class. But I just wanted to complete the theory itself by running through a binary operation um, given as a multiplication table, right? Now, the purpose of this, of course, is just to demonstrate how a multiplication table is read. Well, actually, we did that in the last class, but now how you interpret um, things such as commutative, associative, and so on from a multiplication table, right? Now, a multiplication table could only really be produced for a finite set, right? Of course, if you have a set like the real numbers, you cannot possibly list all of the elements, right? So a multiplication table is for a finite set with discrete elements, right? So for example, here I've given you all the set A, B, C, D, E, F, right? Now there is a little bit of notation in this question here that we didn't really discuss too much in our last session, right? And that is this little statement here. So I just want to kind of focus on that very briefly, really and truly, because it is the least important part of what I want to discuss today. Well, not that entire thing, as a matter of fact. This here, binary operation maps from the set S squared to the set S, right? Now we started speaking about at the very beginning of this topic about operations on the real numbers, right? Now a binary operation, we said it takes two numbers from a set and it performs some kind of computation, and then the result of that computation is a number, okay, or another element. Good. Now it is not really that it takes two elements from the set itself, is it takes a single ordered pair and then performs a, a computation on the two numbers that are contained within the ordered pair, right? So it is strictly speaking incorrect to say that a binary operation, it operates on the real numbers. It actually doesn't really operate on the real numbers. It operates on the set of ordered pairs, let's say X and Y, where X and Y typically belong to the set of real numbers, right? Now this itself here, this ordered pair, it doesn't belong to the real numbers. So X and Y individually belong to the set of real numbers, but the ordered pair, it belongs to the set. And well, I'm just gonna come out and say the set it belongs to, and then I'll explain it after. It actually belongs to the set R squared, right? And I'll explain what that notation means. Another way of writing it actually is to write it like this: R multiplication sign R. So this is actually what it is, to be honest. And of course, you can see why they would call R multiplied by R R squared, right? Now, this set here is what you call the Cartesian product. That's an A there. Duct. Cartesian product of the set R and the set R. Good. Now, when you say you form the Cartesian product of two sets, you are talking about all of the ordered pairs that could be taken from that set, right? So let's say, for example, right? Simple example, I give you two sets. I'm going to give you the set A, which has the numbers, let's say, or the elements A, B, C. And then I give you another set, let's call it B. And I'm going to choose a completely different thing here to work with. Let's call B the set 1 and 2. So those are two finite sets, right? Now the Cartesian product A cross B, or A times B if you want, if you like, is the set of all ordered pairs of the form x, y, where this here, well, I'm writing a sentence, right, where x is taken from the set A and y is taken from the set B, right? So it's all of the possible ordered pairs that could be made from the sets A and B, where the first element in the ordered pair is taken from the set A, and the second element from the in the ordered pair is taken from the set B, right? So the Cartesian product is itself a set, is the set of all ordered pairs. So the Cartesian product of A and B is this set here, all of the ordered pairs. So for example, you could get A and 1, you could get A and 2, right? You could get B and 1, B and 2, you could get C and 1, C and 2, and there actually are no others, right? Because for example, if I give you the element or the ordered pair 1, 2, sorry, not 1, 2, let's say 1A, right? 2, 1 is not there, so let me say 1A. Now 1A, that doesn't belong to the Cartesian product of A and B. Why? Because the element 1 is not taken from A, no, and the element A is not taken from the set B, right? So an ordered pair operates on, or is a function, or is a mapping from the set of ordered pairs onto a singular set, right? So no, I'm just explaining this here because just in case, for example, they give you a question and they don't use their regular notation, right? Now, good. So yes, I just say let me just kind of chuck in some extra notation in this question here, so at least you all will kind of understand if it ever appears, right? So the binary operation operates on the set of ordered pairs obtained from the set of real numbers, right? Now, in the case of, let's say, our regular coordinate system we use where we plot points and that kind of thing, both the x and y coordinate are real numbers. So the pair of coordinates x and y, let's say that you plot on a graph, that belongs to the set r cross r, also written r squared. Okay, so now going back to the question itself. So now that I've kind of explained what that notation means, I'm going to delete everything I have on the right hand side, right? I'll delete it just now. So when they say it maps from the set S squared, it takes all of the ordered pairs where the first element from the ordered pair belongs in the set S, and the second element from the ordered pair also belongs in the set S. It takes that ordered pair and it maps it onto elements that belong to the set S. That's what that notation there means. It maps from S squared to S. So S squared is not A squared, B squared, C squared. No. S squared is the set of ordered pairs obtained from the set S. The first element belongs in S, the second element also belongs in S. Okay, so that is a notation, right? Very abstract stuff and whatever it is, but that's a type of notation, right? Anyway, now in this case here, there is no real computation to do, right? Because the set S is basically letters, right? So you have a multiplication table now that defines what each ordered pair maps onto, right? And I showed you all in the previous class how you could, well, how you should read a multiplication table. So let's say, for example, I want to do A hashtag B, then I take the A from here, and I take the B from there, and I get C. Okay, so the first number here, or the first, well, letter in this case, is taken from this first column, and then the second number is taken from the top row. Okay, that's the correct order of reading a multiplication table. Okay, I mean, we kind of discussed that already. Okay, So the multiplication table defines the result or what each ordered pair is going to be mapped onto. Okay. So they want you to, and I'm going to look at each individual part. Explain why S is closed on the hashtag, right? Explain why hashtag is commutative. What is the identity element in the set S on the hashtag? And then write down the inverse of each element in S, right? Now, it is a very, this question, or this example here contains some very assertive questions. They are basically, oh, I missed out one of them actually. Associative, I'll put it in shortly, right? So it is very assertive in its questioning. It basically tells you the property, but they want you to identify something or explain something about it, right? So it's not that we are really going to search for it itself, except I did want to include one more question here for associative, right? So this one is a little more open-ended, so it'll say is that associative. This one is a little more open. It's not as assertive, right? So it may or may not be associative, right? Anyway, as you say. So explain why it is closed on the star. Well, on the hashtag, right? Well, I mean, I could watch any symbol and call it star, okay? Is it closed? What is closure about? Closure is about when you perform the operation on the set, you get back an element from the same set itself, right? Or in other words, you know, with our new understanding of what a binary operation really does, when you perform an operation on an ordered pair drawn from the set, your answer or your result is a number from the set itself, right? And of course, they gave you the set S is the set A, B, C, D, E, F. So basically, these are all the results inside here from all the ordered pairs. And you notice now that, I mean, it's either A, B, C, D, E, or F. You have there, you don't have any other letters appearing there. So all of these elements here belong to the set S. There isn't an element there that is not in the set S. So there is closure. Every time you perform the operation, you get an element from the set from which the ordered pairs are taken. Okay, so it is closed. So I mean, how do we put that in words and that kind of thing? So this is A part 1. They say explain why S is closed on the star. Is the reason is that the table contains only elements from S. From S. So that is to say, each ordered pair or each element from S squared always maps to an element from S. Yes, and that by definition is closure, right? So part 2, they want you to explain why it is commutative, right? Now remember, commutative is about every time you do X, you do X star Y, and you get the same thing when you do Y star X for all possible ordered pairs in the set. Not only a couple of them, it has to be true throughout the set. We kind of made that point in our last class, right? So how do you do that in a multiplication table? Well, there are a couple of ways you could, for example, explain it, but I want to show you all something here. Now, when you switch around, you know, so you're going from having X star Y and you want to talk about Y star X, it's basically as if you are taking, you know, a row and turning it into a column, right? Now, what in particular you look for is if I, for example, I number the rows. This is the first row, second row, third row, fourth row, fifth row, sixth row, right? And then I number the columns. This is the first column, second column, third column, fourth column, fifth column, sixth column of this table here. If you look at the table closely, you will realize that the first row if you read the first row in order and you read the first column in order, it is the exact same order you are reading. E, C, B, F, D, A. And if you come down here, E, C, B, F, D, A. Right? Now it when you're investigating this, you have to look at all the rows and all the columns. So it's not only the first row and the first column being the same, It's about the second row and second column, third row and third column. All of them have to be the same. And if there is any discrepancy, or if there's anything in your multiplication table, or I'm sorry, let me be more specific. If there's any row of your multiplication table that is not the same as that same numbered column, then it is automatically not commutative. If you look at our second row, CDF, CDF, AEB. And let me go down the second row. I'm sorry, I called out the second row. CDF, AEB. That's my second row. My second column is CDF, AEB. Same thing. Third row, BFD, EAC. Third column, BFD, EAC. Same thing. Same thing right through. Right? Well, I mean, I have a little 3x3 thing here. I check everything else, right? CBD. Same thing. CBD. As a matter of fact, I should check the whole thing. FAE, CBD. FAE, CBD. DEA, BCE, DEA, BCE. Same thing. Everything is the same. Right? So throughout that entire multiplication table there, the first row is equal to the second row. The third row is, the first row is equal to the first column. The second row is equal to the second column. The third row is equal to the third column, and so on throughout that entire table. Right? Now that is one way you could check for it, right? You look at every row, and then you compare each row to its, to its similarly numbered column, and it has to be identical, right? Another way you could do it is this. Now this here is a rectangular array of elements, right? Which basically constitutes a matrix, right? You all learn on matrices when you all were in Form 5, so I'm sure you all heard about something called the leading diagonal of a matrix, right? So this here is a 6x6 matrix I have here. Now if I do the leading diagonal, I start first row, first column, and then I come down like that. Second row, second column, third row, third column, and whatever it is. That's my leading diagonal there. Now if you look on the outsides of the leading diagonal, you go outside there, same thing. Same thing. You see that? So I'm looking now to see if that 6x6 matrix is mirrored with the line of symmetry being the leading diagonal. That's what you are looking for. So you are going out like that from the leading diagonal, right? So you go out this way, FF. You go so FF, same thing. You start here, you go out there, AD, and you go out there, AD, same thing. Right? Follow me? Come here. You go out here now, AB, same thing. Everything. So as you look at your leading diagonal and you look outward, both left and right of the, well, you have to, well, I mean, for me to call it left and right, I have to tilt my head literally, the same angle as my leading diagonal there, right? So on both sides of the leading diagonal, you have the same elements. It is as if the leading diagonal, is like a mirror line for that 6x6 matrix. Right? So that's another way you could explain it as well. Right? So the explanation could be this here. You could say that let's see it like this. So we could say that the multiplication table, let me say table, right? Is obviously a multiplication table. So let's just go say table for brevity. The table is mirrored about the leading diagonal. All right, that's one way you could say it. So that is a sufficient reason. It's mirrored about the leading diagonal. Thus, for all elements belonging to S, for all X and Y belonging to the set S, XY, X hashtag Y is equal to Y hashtag X every time, right? If you switch around any ordered pair like that, they both map onto the same thing, right? So you could say it like that. You could also say that the this one is probably a little bit more troublesome to construct, right? So you could say the ith row is equal to the ith column, right? For I equal 1, 2, 3, 4, and 5. Right? That's like a mathematical way of saying first row is equal to the first column, second row is equal to the second column, third row is equal to the third column, fourth row is equal to the fourth column, fifth row is equal to the fifth column. That's how you say all that stuff there mathematically. So the ith row is equal to the ith column for I being 1, 2, 3, 4, 5 in the given multiplication table, right? So thus, for all x and y belonging to the set S, x hashtag y is equal to y hashtag x. Right, so that is why it is commutative. Okay, so you're looking either for one of two things: for the ith row to be equal to the ith column for all rows and columns in the table. Well, corresponding, I mean, rows and columns in the table. Or you could also look again down the leading diagonal, and if you go outward through the table, you realize it's the same thing moving outward from the leading diagonal of your table, right? That's how you know when you have a commutative operation as defined by a multiplication table. Right, so that's that. That's our part A. Part B. They want you to determine if hashtag is associative, right? Now what do you do? What do you do for associative, right? Now, for associative, recall for associative, you have to show that A star B done first and then star C is equal to A star B star C being done first. Okay. If this is true for all A, B, and C belonging to whatever your set is, then it is associative, right? Now, in a multiplication table, right? Now, I'm not telling you this has to happen all the time, but usually in a multiplication table, if they ask you about associativity, it is not going to be associative more than likely. Now, the reason is that it is very difficult to take a multiplication table and show associativity, because if you think about it, you have to consider every triple of elements, right? Every three elements, every group of three elements you could construct from your set, you have to show that A star B done first star C is equal to A star having done B star C first, right? So it is impossible, really. Well, it's not impossible. It will take us an extremely long time to form every possible triple from the set A, B, C, D, E, F here, right? So because it is that difficult to do, right? Remember, there's no equations and so on for us to work with like we did in the last section, right? So it's very difficult in a multiplication table to really show that it is associative, right? So in a questioning setting, it will be a case where you get something that is not associative. Because for not associative, that doesn't have to be a set wide property, right? If you have a binary operation that is not associative for a single combination, then that is sufficient to say it is not associative, right? You only need one counterexample to say that it is not associative. And this holds for commutative as well. If there is a single case, right, no matter how many ordered pairs you could possibly get out of the set, if there is at least one that does not have that demonstrates, something not having the property of associativity or commutativity, then in that case, that is enough to say that it is not a commutative or not associative, right? So what you do in a case like this here is you can basically take a shot in the dark now and hope that what you choose does not work out, well, works out in such a way that it is not associative, right? Now, if you choose three elements and and it works out to be associative for those three elements there, then that is not overwhelming evidence. Remember, this is not a formula. We don't have a formula to work with. We can't generalize the outcome of every ordered pair here because it's letters. There's no formula to follow, right? Unlike what we were doing before in the last section, right? So we are basically going to form A star B. We are going to do that and then star C and see what we get. And then afterwards, I'm going to do A star and then, well, I'll do B star C first and then A star, the result of that. And hopefully I'm going to get different answers, right? So A star B is what? I do A star B. It is A star B is C, okay? So I end up with C star C, right? So let me go and do C star C now. C star C is D. So the result of this one is D. So I'm hoping and praying now that the result of this isn't D, because if it is D, I haven't really proved anything, because A, B, and C are actual specific triples from this set here, right? Obtained from the set S, right? Anyway, so A star B star C. So I need to do A star, and I have the result of B star C first. So B star C is equal to F. So A star F is what I'm going to do now, right? So I'm going to do A star F, and what do I get? I get A. So the result of this one is what? It's different to the result from before. So what I could go on now to say is this means that A star B first, and then the result of that star C is not the same thing as A star, the result of B star C. Okay? This means what? That, I'm putting star, but it's really hashtag I should be putting there. Hashtag is not associative. Right? I have to go back here. I've been putting star because star is the usual symbol we meet. But in this particular question here, they gave us a different symbol, so we should probably be using, not probably, we should be using the symbol that they gave us in the question itself. All right, so I should be using that hashtag looking thingy there. All right, so A hashtag be done first, and then the result of that hashtag C is not the same thing as A hashtag the result of B hashtag C. So it is not associative. Okay, usually in a multiplication table that happens, because otherwise, I mean, we will have to exhaust all possible groups of three, right, for us to then say that it really is associative, right? So going on now, part C was the identity element, right? Now remember, the identity element is such that when you perform the operation, take any element from the set, form it with perform whatever operation with the identity element, you're going to get back the same result. So A star something, and you get back A. A star, the identity is A. B star, the identity is B. C star, the identity is C. D star, the identity is D, and so on, right? Now, in the last section as well, the general symbol for identity is E, right? The general symbol for identity is E. So like, based on what we were doing before, if I were to just jump back to that a little bit, right? When we were doing, for example, or searching for our identity, right? We will just say, or suppose the identity is E. So E is like a symbol you use, right? But I mean, remember in that last section that we were talking about real numbers. So A, B, C, and whatever were numbers, right? Well, this question here is literal, right? This question, the set from which you are drawing whatever it is an actual set of letters. So E is an element from the set. right? So it's not because that element is E means it's automatically the identity, right? The, right? You can't how to say be hard and fast with symbolism like that. E is a symbol for the identity, but it doesn't mean in this set here because that we have an element called E. It has to be the identity, yeah? Right? So don't fall into a trap like that, right? Because what you have to search for is the property of the identity. It's not about the symbol, it's about the property, right? So what you are looking for is there element where every time I perform A star that element, I'm going to get back A. Where do I get A star something being A? Look, I get A star what? F is E. Follow me? B star, the identity has to give me back B. B star F is also B. So it seems as if F is the identity, right? So you can't just look and say, hey, look at our E there, that has to be the identity. No, right? They could easily, lay that trap for you and you fall into it, right? Now, identity also has to be a set-wide property. Every element has to have the same, the identity is a singular fixed element from the set. So it has to work for every member of the set. Okay? Now this set here is finite. We know all of the elements A to F, A, B, C, D, E, F. So basically, how I could do identity is like this here. I could do so. I have to do something set wide. So I'm gonna circle the entire set here. A, B, C, D, E, F. And I just go down my table and look to see where I literally have A, B, C, D, E, F in that order. And where do I get it? Well, I mean, you can already knew it was here. So what you do is you take this heading, this left heading here, and you look to see where it is repeated down the table, and it is repeated there. So it means that this is the identity, right? Now, in a general sense, you also have to do it with your rows, because we defined identity as A star E has to be E star A, and it or both of them have to give you back A as the answer, right? Now, when an operation is commutative, though, you don't need to investigate E star A, having investigated A star E. I'm talking about the generalized E now. The symbol for identity E in a generalized sense, right? So I don't need to go and repeat it for the rows because if it works for the columns, it will work for the rows because the operation is already commutated. Okay, so I take my whole set in order and I look to see where in order it is repeated. It's repeated down here, A, B, C, D, E, F. Now I have A, B, C, D, E, F in every column of this table, of the results, I mean, right? But only one place it happens in that same order. So A star F is A, B star F is B, C star F is C, D star F is D, E star F is E, F star F is F, in that order, right? So they just need to, all you need to do is identify the identity element, right? Not because we have a C, so an element called, I'm sorry, A, E. Not because we have an element called E means it's automatically the identity, right? So here the identity element is F. Why? Because anything from the set star F gives you back the same thing. Okay? We don't need to say more than that because they just said what is the identity. Write down the inverse of each element. But right now, inverse now, you could only speak about inverse. You could only speak about inverse if there's an identity. Right? Question is assertive. Right? It says what is the identity, so that means the identity was there in the first place. They want the inverse of each element, right? Now, the inverse of an element is such that if you perform the operation of an element with its inverse, you get back the identity, right? So what I'm trying to do, for example, if I want to get the inverse of A, I will have to see A star what is going to give me F. That's what I'm looking for. A star what is F? Because F is the identity. A star, its inverse, will give me the identity F. So that's what I'm looking for. So I start off with A. Where do I get F here? The result is F here, so that means the inverse of A has to be D, right? So well, I could do it like a table. So I could do all of the elements A, B, C, D. You know, as a matter of fact, I wouldn't do it with the table. I will do it with the notation. So let me write down the inverse of A. Inverse of A is what? D. And let me put the reason here. Because A, well, it's not really star, is right? It's hashtag, right? A hashtag D is F. F is the identity. That's the reason why. Okay. What about B? What's the inverse of B? Like, look, I start off with B here. Where do I get F? I get F over here. So it means that C is the inverse. B inverse is C. Again, because B star C. B star C gives me F, which is the identity. C inverse was the inverse of C. The inverse of C is B. That was kind of expected. Why? Because the operation is commutative. If B is the inverse of C, then C has to be the inverse of B. Why did I put an inverse there? Sorry. B is the inverse of C. Because why? C was the inverse of B. The operation is commutative, right? And there's a reason for that. So when I go to the inverse of D, I kind of expect the answer to be A because the operation is commutative, right? But let me just verify. It was the inverse of D. Where do I get F? Right next to it here. So that means the inverse of D is A. Okay. So that happens with a commutative expression. Sorry, with a commutative operation. If one element, well, you don't really say inverse of element. You say two elements are inverses of each other, I should say. So like for example, multiplication, I could say a half is the inverse of 2 under multiplication. But I could also say that 2 is the inverse of a half, right? Under multiplication. Anyway, what about E now? Inverse of E, I have to do this here now. Inverse of E is what? Where do I get F? Here. A. I don't have F anywhere in this row. So you know what that means? Inverse of E does not exist. Because nowhere do I have E star something be in F. It simply doesn't happen. Right? So E inverse does not exist. And I actually have something to say about that afterwards. What about the inverse of F? Well, the identity is the inverse of itself under the operation. Right? So, I mean, if I start off with F, where do I get F? Over here. So what's the inverse of F? That. F inverse is F itself. And that happens, right? Now I have a few how to say, I have a few points to make, right, with respect to this thing here. So for example, first of all, I want to mention here that 2 points, right? The inverse of the identity is also the identity. Right? That's one kind of obscure point I want to make. Right? And the other thing I want to make about this here. I'm actually not going to write it down. I'm just going to speak about it, right? Now, E inverse does not, you know, E does not have an inverse. That is like, for example, the number, you know, in the number, in the real numbers, you have a number called, obviously you have a number called 0. 0 has no inverse under multiplication, right? There's no such thing as the inverse of 0 under multiplication. Why? What is the identity for multiplication? The identity for multiplication is 1, right? I cannot multiply 0 by anything and get 1. It is simply not possible, right? So again, the inverse of an element is such that when you perform the operation, of an element with its inverse, you get back the identity. So for example, in real numbers, now you have a number called 0. 0 has no multiplicative inverse because it's simply not possible to take a number, multiply 0 by it, or multiply it by 0 and get the identity for multiplication, which is 1. So that this E here is playing the role of a 0 in this set S here. Right now that is actually not on the syllabus itself. Zeros of an operation is not on the syllabus, right? But anyway, so that's why I'm not writing on that point. I'm just saying it, right? So that's basically it for this particular lesson here. What we'll have to follow it is probably some further worked examples, right? I still also have to upload that video for you all, where I go through the solutions of the worksheet that I give. So you all will have to look out for that one afterwards, right? So there are two videos I want to follow up this one with. Number one is further examples on this topic here, and then the solutions to the worksheet itself. So that's all I have to talk about today.